Hello everyone, welcome to VLSI Toolbox channel. Today I will be talking about standard cell layout using Euler path optimization. We can use this optimization to optimize our layout and so that it may be a compact and generate less parasitics. So without wasting time, let's check it out what is called standard cell layout. The standard cell layout structure is shown here, which I have taken from this URL noted mentioned below. The height will be fixed. The layout height will be fixed for a particular PDK, and BTD width, bus width, and BSS bus will be fixed. Width is fixed, and PMOS and MOS has separate area allocated. We can use this area. Within this you have to design, and corresponding internal gate wiring and IO connects can be done within this standard cell height or this area. So there is a constant in height, but you can use variable width depending upon your requirements. So let us see what is the approach of Euler path optimization. And now let us see what is the approach of Euler path optimization. The main objective of this method is to keep a single diffusion for PMOS and another single diffusion for NMOS separately with no breaks, and poly runs vertically. Basically, with this method we are finding the order of inputs after which input we have to keep which one. So that is, if a circuit has a 4 variable, then A, B, C, D, then after A plus A, then should we keep B or should we keep C? These things are decided in Euler path optimization approach. The rule is each transistor must touch electrically once next to it. First start with some transistors separately for PMOS and NMOS and trace the path through rest of the type without rising pan, crossing each gate once. This is the rule. It may require trial and error and rearrangement. So let us see graphically how can we optimize Euler path. So this is the Euler path demonstration. Here you can see I have marked the two paths for PMOS. One is A, B, C, D, and also here A, B, C, D. Both the PMOS and NMOS have similar paths according to our rule mentioned previously. So here you can see A, B, C, D. This PMOS and this are touched once by a single path. Again here from A we have go to B, then C, then D. So for this expression, a Boolean expression or Boolean circuits or digital circuits, ABCD is the common path for both PMOS and NMOS. So we will follow this in the layout. So it will be A here, B here, C and D. This is polysilicon, the gate. So we are using the orientation order A, B, C, D as my orientation or the path according to our Euler path solution. So this yellow one is the diffusion for PMOS. This is green one is the diffusion for NMOS. So it's a single diffusion for all the MOSFET, that is for NMOS and PMOS separately, and this is the metal for connecting BDD and BSS. So in this way we can arrange our layout and optimize our layout so that we can get less parasitics after parasitic extraction. So let us solve a more complex example so that it can be very much clear to us you. So this is the expression given, and we have designed the circuit according to this expression. Now let's trace the Euler path. First consider CBADE. CBADE. So C, after the D, then A, then D, then E. So it's okay, but you can see here CBA. So it is not okay for PMOS. So it works for NMOS, not for PMOS. Next, again let us check for another path, CBDEA. CBDEA. So let's erase the ink and redraw the path with this order: CB, C, CB, D, E, A. So it is okay for PMOS. Next, for NMOS, CB, D, E. So it's crossing, so it's not applicable for NMOS. So we have checked two orders. Let's check another. So let's check another order, BCADE. So BCADE. So it is okay for NMOS, and here for PMOS, BCADE. Yes, this is okay for both the MOS. So we will follow this order to do our layout and optimize our layout so that we can get less parasitics. So let's move on to the Cadence itself and see the implementation. Now let's open the design in the Cadence, and here I have opened my design. The example that we have just solved just now is shown here, and we will now generate the layout and do the layout according to the order that we have obtained from Euler path optimization. So let's start. Go to layout Excel. Set the grids. The grid setting is very much important. Here I have set the grid for UMC 180, that is 0.001, 0.01, 0.001 for X snap, Y snap. Now go to connectivity, generate all from source. No need to generate a pins PL boundary, it can be created later on. I have pins, only instances I am generating. Okay. So these are the MOS. Press Shift F to view the layers. Now let's position the PMOS and NMOS separately according to the orientation. So you can zoom it and check the pin number. Here it is written D. You can see here D. Here it is written E. So first, which bit? B we require. So for B, check B. So this MOSFET is B MOSFET. We first keep the B MOSFET here, and then check it for C MOSFET. This is C. You can see here C. Then you place the C after B. Now next A. Which one is A? This one is A. This one is A, and after that D. So this is D. This is D. Next E. So this is E. Remaining one is E. Okay. Now position the NMOS also. B C A D E. B MOSFET is this. B terminal, gate terminal is there. B, then B C is there. B C. C, B C A. So A is there. Next D. Then E. Let's move further. In layout, alignment is very much important. So keep your mouse in proper alignment. Otherwise, it will may cause or generate more parasitics. This is net 4 and this is also net 4. So check it. If it is same, then merge it. Press R, click on this, then it will show the fly lines. So you can merge these two together. Check the alignment. Next, this is what out. This is net 3, so no merging. Out is there. You can flip this MOSFET. You can flip this MOSFET. You can flip this MOSFET and merge it because the terminal is same. Out. Now again see the VDD. Here net 3. The net 3 is here. So you can also flip this terminal. Net 3. So you can merge it. Alignment is very much important. Now BTD net 3. So BTD is there. Now I have done the positioning of PMOS. Let's do for NMOS similarly. So BSS is there, BSS is there, this is BSS. You can see here BSS is written. So let's flip and connect to BSS here. BSS here. Next net 1. Net 1 is here. So you can use this orientation. Next net 2 and this is P out. So you can rotate this horizontally to line this in. Next is VSS, and this is net 2. So you rotate this. So the positioning of NMOS is over. You can see here I have aligned the MOSFET for both PMOS and NMOS in a single division. So in a single division, if you want to see the division, press no view and select division. Select from there. Select diffusion from here, diff layer, and press no view. So you can see here this red one is that is diffusion. For both PMOS and NMOS, I have aligned the MOSFET in single diffusion. This is the objective of Euler. First, that we have to arrange the PMOS and NMOS in a single division. Now you have to maintain that height. So suppose I am keeping from SCL 180 nanometer PDK, they have given the specification of standard cell height for 5.6 micrometer. So here I am skipping these things here. Suppose this. So this is with VDD and VSS. So VDD and VSS height is 0.74. So let's draw the VDD and VSS line with MU1. Let's try with MU1 for convenient. So this is for VSS, another line is for VDD. Let's check the width, because they have given the specification of VDD as 0.74. Width is here 0.24, so let's increase it to 74. And this is specification given by SCL 180 nanometer technology. Alignment is very much important, so keep the MOS in proper alignment and your corresponding layer. Now position the PMOS similarly, so that it may accommodate the VDD also. Press S to stress and adjust the So in this way you can arrange your layout and do the connections accordingly. Now as we have aligned our gate to the PMOS through Euler method, you can see here it is marking BCADE. So you align the PMOS as it is not properly aligned. So here it is BCADE alignment. You can see here. Now connect the VDD VSS. Here you can see VDD VSS is there. You just connect. Next your net connection is there. Out is here. So for out you can use here. Out connection is done. Similarly net 3 and net 3 should be connected. So here also you can use another metal instead of using this. VSS net 3 net 1 and 2 is there. Net 1 and net 1, yes, you can use another metal. You have to check the alignment properly. As you can see here, some alignment problem is there. So finally alignment is over. Now you can do the rest of the bearings. Suppose this is net 3, so you have to connect with the net 3 here. So use different metal. For using different metal, press wire, M1 M2 wire, keep it here. So net 3 is there also. So we can use this M2 wire to connect this. So this is the net 3 connection is done. Next is net 1 versus net 1 connection. So we have to give again by M1 M2 wire. Let's give some other metal there. Let's go stack M3 wire, metal 3 I am using here. So M3 net connection. This is net 2 already done. So save it. All the connections I think over. So you can, this is your out, and you can use this path also for net 3 connection, and also this path. So in this way you can do your layout with optimized in an optimized way, and after this you can create your pins and do the verification steps accordingly. So this is it. I have shown the layout process, and using Euler method I have optimized the layout of a standard cell, and I have kept the standard cell height as 5.6. I have pick a value from PDK, that is SCL 180. So depending upon PDK, here I am using the UMC, but I don't have the values of UMC 180 standard cell height. So I am using the SCL 180 nanometer standard cell height, that's 5.6. So depending upon your PDK, you can use your uh, standard cell height and maintain it accordingly. So accordingly, VDD width is also, we have to maintain the VDD width, VSS width depending upon the PDK, and follow this method to optimize your standard cell layout. So I have done the implementation of Euler path method or Euler path optimization technique in standard cell layout in Cadence, and shown the layout. You can do other examples, and if you feel any doubt, you can comment me in the comment section, and hope you like the video, and please subscribe my channel so that you can get more these type of videos that may helpful for your research or any other project purpose. Thank you.